computer. Ooh, the sound. My computer, for some reason, restarted itself last night, and I don't know why. I think it's because I was doing an iMovie for the lab class, but everything seems to be working very quickly today, so that's a good thing. So we're going to do Module 11 today, and we have 2 lectures next week. We are scheduled to be here on Monday and Wednesday of next week, and we're going to use those 2 days. There's a total of 3 lectures in Module 11. 2 of them are going to be on the alcohols. 1 of them is going to be on ethers. There's only about 15 slides on the second one, but we're going to actually learn a little bit about them on the way there. But I want to reinforce some stuff in that last chapter. Now, that homework will not be due until coming back from Thanksgiving break. So you don't have to do it rapidly. We can actually, I think I'm going to make it due on the Wednesday of that. Because of the schedule. Let's see, where's the schedule? Yeah, I'll still make it due on that Monday because our next exam is on that Wednesday. So I want to have that homework done and available for you to review it for our exam. Okay, so exam 3 is going to be over modules 8, 9, 10, and 11. And it's going to be Wednesday on Top Hat. It'll be the same format as last time. We're going to do that with Top Hat. It's going to be multiple choice questions. And in addition to our review on Monday of next week, I'm also going to have a group activity called reaction tables. This is a great time to start reaction tables because we're going to learn a lot of reactions in addition to the ones we already know. And we're going to start getting confused. So I want you to use this as a study tool to keep in track all of the reactions. In fact, you'll end up going back to the beginning of the semester and all those reactions with alkenes and alkynes and all that, and start adding to it, and then have that as a review sheet for you. When we go to next semester, we're going to add probably 5 times more reactions to that sheet. And so it's a good way to organize. It's a good way to remind yourself what they are. And I'll show you how a good way to build one yourself. And you have to build it yourself because you have to organize it yourself. So you can go download them and that's fine and dandy and it's a PDF and all that. But if you build it yourself, you will understand it a lot better. Okay, so any questions on administration so far? Chat room is open if you have a question. My soundboard seems to be working quite well today, so go ahead and ask questions as needed. So what I'm going to do now is I'm going to go ahead and start sharing my slides and go over module 11.1 alcohols. All right, so share my screen. All right, you should be seeing my screen here pretty soon. Again, these slides are posted both on Canvas and on Top Hat. So if you can't find them on either of those locations, please email me. All right, so in chapter 2, we talked about naming of alcohols and the difference between primary, secondary, and tertiary alcohols. So don't forget to go back and remind yourself how to do that. They're one of our lowest functional groups. And if you have almost any other functional group, like a carbonyl, a ketone, some kind of carboxylic acid, it's going to be named for that. And then it's just going to be that pendant hydroxyl group. But we're going to talk about these alcohols in particular and some of the cool reactions we have around them. So the first thing we need to think about alcohols is, in the acid-base chapter, we learned that the alcohols are about the same pKa as water. And water can act as a base or as an acid. And likewise, alcohols can act as a base or an acid. When we think about that, we have to think about, oh, okay, well, about the same pKa. So we can use it as a way to trap hydrogen, a proton in a solution, or we can actually give one up. So it can be used in any of those systems. There's an arrow on the slide here. This arrow should be pointing in this direction here. So in the presence of an acid, it'll protonate that oxygen, giving you that alkoxium ion. Okay, so that's a nice source of proton we can use for a lot of different catalytic systems. If we remove that proton right here, we get that alkoxide ion. We have a good nucleophile and a strong base. Any kind of molecule that does this, that can be either both acidic or basic. We call them amphoteric, meaning that like water is amphoteric because you can use it for either one depending on what else is in the solution. So it's good that we can do that. We've already used that before looking at the alkoxide as a strong base in our elimination reactions and also in our SN1, SN2 reactions. But now we're going to look at it as in a different way. Okay, so in this module, we're going to look at several different types of reactions. We're going to look at nucleophilic substitution reactions, and this is an SN2 reaction to produce alcohols using Grignard reagents and acetylide. Basically, we're making carbon anions that are acting as nucleophiles. So that's where we're going to start. We're then going to do reduction of carbonyl compounds to alcohols. And we have a couple different ways to do that. Most of it involve the use of a hydride, and we'll talk about that as well. We'll also look at oxidizing alcohols. So using it as the reactive group we're going to oxidize, and we can oxidize them down to carbonyl compounds, but there's a couple restrictions there. One, you can go too far, so we need to think about selectivity and what you can produce based on the alcohol you have. Then we'll probably not get to this till Monday, but we'll have the ring opening reactions to produce alcohols, and then conversion of alcohols to better leaving groups like halides. So let's start off with this nucleophilic addition to make alcohols. So the first thing we have to do is we have to make our nucleophile, okay? So the first nucleophile we're going to talk about is called the Grignard reagent, okay? The Grignard reagent is basically the creation of a very polar bond between carbon and magnesium, and that very polar bond has a high ionic character. It's still a polar covalent bond, but because carbon is the more electronegative atom and magnesium is the more electropositive atom, most of the negative charge resides on carbon, turning carbon into our nucleophile, okay? So we can do this reaction very easily with one equivalent of magnesium and an alkyl halide, an aryl halide, even a vinyl halide. They all create these Grignard reagents. Now, notice that all of these use the word ether in here. These reagents are not easily stabilized. They can easily break apart, and so we use ether to help stabilize this complex. Number one, we make them in ether. Number two, we use them in ether because they are not very stable, and this keeps them from falling apart and allows us to use them as the good nucleophiles they are. The other way we can create a nucleophile out of carbon is to use an organolithium reagent. And in this one, instead of using magnesium, we're going to use lithium. And again, carbon is more electrophilic than the lithium. Therefore, most of the negative charge is on that carbon. However, it's still a polar covalent bond. And we can make these lithium reagents in a similar fashion, starting with a metal. We can make them in ether as well, and it'll break these sigma bonds and giving us our ether reagent here, our lithium reagent here, and a strongly charged carbon. And that strongly charged carbon is our nucleophile. Okay, so why do we need the ether there? Well, in the Grignard reagent in particular, the oxygens of the ether help stabilize that positive charge on magnesium. And when they stabilize that positive charge on magnesium, the complex is more stable and it stays in solution more, so we can use it as our nucleophile. So how do we do this? Well, notice we start with metallic magnesium. Magnesium with its complete shell of electrons around it. It's not magnesium plus 2, which is the state it wants to be in. So the mechanism involves the actual oxidation of magnesium is going to transfer 2 of its electrons to the bond between the carbon and the halogen to create a new sigma bond. And both of those electrons from that new sigma bond came from the magnesium. So let's look at that stepwise here. So the idea here is it kind of follows a radical mechanism where one electron is donated and then one of the electrons from the sigma bond is donated to create a new magnesium halogen sigma bond, okay? So that leaves one unpaired electron on magnesium and one unpaired electron on the carbon. So as we found out in the radical chapter last week, we saw that those like to do a termination step by having a radical-radical combination to give us a new sigma bond. And when we do that, we end up with our Grignard reagent. Notice that our magnesium is now magnesium plus 2 because it's given up 2 of those electrons. So it's magnesium plus 2. So if we were to like try to balance charges here, our halogen would be -1 and our carbon would be -1. Okay. So with all our charges balanced and these strong polar bonds, we can now use it as our Grignard reagent. Things are a little simpler in the lithium reagent. We only have 1 electron to transfer from the lithium. So we actually have to have 2 equivalents of lithium to do it. 1 to make the bond with the carbon and 1 to make a bond with the halogen. So you actually end up with the lithium halogen as a byproduct and 1 equivalent of your organolithium reagent. Now these don't need that stabilization to maintain that lithium ion. It's a smaller ion and it's only has a +1 charge. And so we can actually make these organolithium reagents in things like hexane or butane or toluene. So they don't have to have that ether in them that is practically a requirement for all of the Grignard reactions. Okay, so do you see how we made these reactions now? Yeah, okay, all right, moving on. All right, so how do we use these? Well, so I said it's still a covalent bond, but it's very polarized. And so it has a slight ionic character. In the lithium, it has approximately a 40% ionic character. So that's a very elongated bond with a partial charge on carbon as a negative ion, a partial negative charge. And on the lithium, it has a partial positive charge. Okay. So if that were to ionize, it would end up giving us a true nucleophile with a negative charge on our carbon, and then a counterbalancing positive charge with the metal. The same thing would happen in the magnesium here, but it's not as strong as ionic character is. So it is a little less nucleophilic than the lithium reagents. Okay. So if it does do this kind of, if it's in this resonance structure forming this negative charge on carbon, well, what does that look like? Well, we talked about this last week as well. We know carbocations are trigonal planar and they have an empty p orbital above and below that plane. And we said when we add a radical to that unhybridized p orbital, it tilts it down a little bit because of electron-electron repulsion. Well, now we're actually in our resonance structure creating this carbanion, the negative charge on carbon. And both of those electrons are going to be in that same orbital, pushing those 3 substituents down. And so it almost is trigonal planar, but they're pushed down a little bit because you have 2 electrons doing the full electron repulsion. So in our resonance structure of our compounds above here, we can imagine that our carbanion, or the carbon nucleophile, is going to look something like this. Okay, so how can we use it as a nucleophile? Well, we're going to use it as a nucleophile because it's going to want to attack anything with a positive charge or a partially positive charge. So if we think about alkenes, neither one of those sides is really partially positive. That's a nonpolar bond. So it's kind of just sitting there, right? However, in the presence of a carbonyl here, our resonance structure suggests that we have a part of the time a positive charge on carbon, part of the time we have a negative charge on oxygen, leading to our hybrid structure of that partially positive carbon on a carbonyl. So now we have a target for our nucleophile. Okay, our nucleophile is going to want to attack the carbonyl carbon of those compounds. Okay, so what does that look like? So because we have that partially positive carbon of that carbonyl, and because we have that partially negative carbon of the Grignard reagent, we're going to make a new carbon-carbon bond, a new carbon-carbon sigma bond. with those electrons that we get from this carbon here. Okay. When we do that, the magnesium bromide salt needs to be counterbalancing. Well, luckily, we have the electrons popping up from the carbonyl double bond, giving us a full negative charge on oxygen and generating a salt right here. So then the reaction just stops until we acidify the reaction at the end and break up that magnesium complex. Okay, so there's always a second step in the Grignard reaction, usually dilute HCl to generate our free protonated alcohol and some magnesium salt. Okay, that can also be written as just hydronium ion or hydronium ion in water. Okay, we'll see that a lot. Okay. So there's always that second step in the Grignard mechanism. All right, any questions on that? So one thing I want to note here is that in this particular reaction here, we have a carbon sigma bond, a carbon sigma bond, and a carbon sigma bond. So those are all very strong bonds, and those carbons are all very bad leaving groups. So the reaction stops right here. That changes when we have other functional groups in those positions. All right, so that makes Grignard reagents really, really useful, okay? Because we can do a variety of things. We can make primary alcohols, secondary alcohols, or tertiary alcohols just by starting with different carbonyl compounds. We can even make a carboxylic acid looking at a different carbon compound. Let's start with the first one. If we have the simplest aldehyde possible, which is formaldehyde, it's got 2 hydrogens on it here. Those hydrogen groups are going to stay on that product. All we're doing is adding a carbon to the carbonyl compound and giving our negative charge on our oxygen, which then gets protonated, okay? So these 2 hydrogens on our starting material end up on our final product, giving us a primary alcohol. So formaldehyde will give us a primary alcohol after acidification, okay? However, all other aldehydes will give us secondary alcohols. So we only have 1 hydrogen on our other aldehydes here. That hydrogen stays there. We have attack by our nucleophile, generating our new carbon-carbon sigma bond. After acidification, we have the original R group, the original hydrogen on our carbonyl compound, plus the carbons from our nucleophile. So all other aldehydes generate a secondary alcohol. Okay, so what if we don't have any hydrogens? Well, that's a ketone right here. And so we're going to end up with 3 carbons on that carbonyl carbon at the end of the reaction. And when we have those 3 carbons on that 1 carbon, that makes it a tertiary alcohol. Okay, so do we see how the only thing being attacked in all of these is the carbonyl? No other groups are leaving. Okay, and at the end of the reaction, when we acidify, the oxygen is protonated to give us those alcohols. All right. So what if we take the most oxidized carbon we have, which is basically CO2. You can think of it as 2 carbonyl compounds, right? Carbonyl on one side, carbonyl on the other. Well, turns out that carbonyl reacts with these Grignard reagents as well. We can have that Grignard reagent attack at that central carbon, and then it's going to give us this intermediate here, okay? One of those oxygens has the negative charge on it. The other oxygen keeps its carbonyl intact, okay? So if we attack it with 1 equivalent of that Grignard reagent, we'll generate this compound here. And then once we acidify, we end up with a carboxylic acid. Okay. Now, other thing to note is that this carbonyl, because it has this oxygen on it, that salt there, is not susceptible to attack. It will not go further and create a secondary or tertiary alcohol. It will stop at that carboxylic acid. Okay, so this carboxylic acid, this salt right here, is stable to these conditions. All right, so that's one of the cool things about this Grignard reagent. So now we have our first carbon nucleophile other than our acetylene ion, and we're able to build these structures and give us multiple different forms of primary, secondary, tertiary alcohols or carboxylic acids by choosing what we're attacking with. what we were attacking with our Grignard. Okay. So to really put a really fine point on the mechanism, it's just another set of mechanisms where we have nucleophilic attack with onto an electrophile. Okay, so we're going to have that nucleophile, that full lone pair is going to come in and create our new sigma bond. Then our pi bond is going to be broken, giving us our lone pair on that oxygen, and then after protonation, we get it to the, we get the acidic protonation, we get to the free alcohol. Okay, so notice nothing else changes. We did these attacks before with other nucleophiles in our SN1, SN2 chapters. Okay, now we just have a new tool in our toolbox. And the great thing about this is that you can make those Grignards out of any alkyl halides, aryl halides, or vinyl halides. So your ability to create these different carbon structures is enhanced because we can do this. Okay. So, you might remember, well, esters had a carbonyl. Does it attack those? Well, yes, it does. However, it's a little bit different when we use it with esters because we end up having something that's a pretty good leaving group in the intermediate, and that changes the final reaction. Okay, so let's look at that in detail. So if we start with just our Grignard reaction and we attack our carbonyl, notice this is not the salt. This is an ester here. The carboxylic acid salt is not reactive to this, but esters are because we don't have the negative charge here. The first thing that's going to happen is we're going to have attack, creating our new sigma bond, and we'll have this intermediate here. Now, if we don't acidify, we can do additional reactions because we now have the alkoxide as a leaving group. Okay, our Grignard reagent is a really, really, really strong base. Our alkoxide is not as strong. So in this case, it is a better leaving group than those carbanions that would be formed in the other thing. So it does leave. When it leaves, the electrons from the bond with the magnesium kick in and regenerate a carbonyl compound. Well, we have another carbonyl. If we have one more equivalent of Grignard reagent, it's going to react just like it does with ketones. And so the second one is going to react with that ketone, and it will generate a tertiary alcohol after protonation. Okay, so the cool thing here is you can take an ester and two equivalents of Grignard and generate your tertiary alcohol because it converts to a ketone in the middle of the reaction. All right, questions on that? So we can make tertiary alcohols two ways. We can make secondaries and primaries one way, and we can even make carboxylic acids all with the same reagent. Okay, so the mechanism is like I defined it there, is stepwise. We have our nucleophile attacking our carbonyl compound. Once we form our carbonyl compound, we have that anion over here on our oxygen, which then can come in and regenerate our carbonyl and kick out the alkoxide ion. Okay. Now that alkoxide ion is not as nucleophilic as our carbanion from our Grignard reagent. So the Grignard reagent will come in and attack that carbonyl. And we actually have generated a new tertiary alcohol here. Notice that we have some control over the final product ratios, because the final product, because if we have two equivalents of the nucleophile, we know we're going to add those two R groups to a tertiary alcohol. So if we had this as a hexyl group and we hit it with methyl Grignard, we'd have dimethyl hexyl alcohol, or in this case, it would be methyl heptanol. So we can do that using control of our nucleophile and our substrate. Okay, so turns out that we can also use them as strong bases. Now, what is that Is that useful? Well, it's a problem actually, because if there are any acidic protons in your solution, it will immediately react with those first, meaning you have to control what kind of other functional groups you have in it. So if you already have an alcohol in your system, the Grignard is going to react with that alcohol and deprotonate it. If you have an amine in that system, it's going to deprotonate that amine and stop the reaction. So we have to be careful about what we use because it's such a strong base. Okay. So what we will see here is if you have your system contaminated, it acts as a Bronsted-Lowry base and will, the negative portion, negative carbon will attack the electropositive side of water, which is the proton, giving us back our hydrocarbon. So if it's a hexane Grignard, it'll give you hexane, the molecule. In this case, it's going to give you back your bare benzene. Now, the fact is that this proton transfer happens much more rapidly than this nucleophilic attack. So any contamination by water stops the reaction cold. Now, we can actually use that to our advantage if we look at trying to figure out where that last proton is going. We can change the reaction by tagging it with a different isotope of hydrogen. In this case, we're going to use deuterium. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron. And cool thing is, it's NMR inactive. So we can actually be sure that where that deuterium is and where that nucleophile was formed in our system. So let's see how we can use that here. In this case, we have our tertiary alkyl halide here, and we're reacting that with magnesium to make our Grignard reaction. And we want to make sure that it formed that Grignard reaction. And so we can test our Grignard reaction by adding the deuterated form of water to give us this deuterated compound here. Now, we can then take that compound and look at it by NMR and know that that proton is completely gone and we won't have any splitting. We'll just have a singles peak for all of these methyl groups. Okay, so we can use that, the basic quality of these Grignards to our advantage to help look for control in our reactions. Okay, so just like the Grignard reactions, they are very, very strong bases. And so we can actually use them to deprotonate acetylene. In chapter 8 and 9, we looked at having the acetylene be deprotonated by sodium amide to give us our acetylide ion. And we use that as a nucleophile, okay? Well, turns out that the Grignard reagents and the organolithium reagents are much stronger bases than the sodium amide here, and will do the same thing. They deprotonate that acetylene proton and will generate a nucleophile out of our acetylene. Okay, so when we do that, we can use any of these reagents as our nucleophile and attack any carbonyl compound. So when we attack those carbonyl compounds, we'll end up creating our new sigma bond right here with those electrons. And when we protonate it, we'll see we have, in this case, we would have our acetylene with an extra carbon and an alcohol at the end. So now we have an internal alkyne that we could probably go and do additional chemistry on. Okay, but it all has to do with the basicity of the Grignard and the organolithium reagents being very, very basic and able to deprotonate the acetylene proton. All right, questions on using Grignards and organolithiums as strong bases? Okay. So we've used them as nucleophiles, we've used them as strong bases.
So I have a question. So Grignards will always, if given the opportunity, act as a base before acting as a nucleophile.
If there's an available proton, proton transfer is typically faster.
Right, okay.
Proton transfer, it will basically take every acidic proton out of your reaction first, and then it'll start reacting with your carbonyls as a nucleophile.
Okay, cool. Thank you.
All right, so that is making alcohols by attacking carbonyl compounds. So now let's look at it a different way. Let's take a carbonyl compound and add hydrogen across it. So we're going to be making alcohols by the reduction of carbonyl compounds. Okay. So the first thing we have to remember is that we talked about this oxidation state when we talked about the alkenes and alkynes. So we have to remember that we have this spectrum of oxidative states. And on our lowest oxidative state possible, we have methane at our -4 because it has 4 hydrogens on it and no oxygens. And our highest oxidation state turns out to be CO2 because it has 4 bonds to oxygen, which gives it a +4. Now, everything else is somewhere in between. So we have ketones and aldehydes are going to be in the +1, +2 range. Carboxylic acids and carboxylic acids are going to be in the +3 range. So we're going to take those higher, more oxidized materials and reduce down the carbonyl to the alcohol. So that's the next step, going from just adding 2 hydrogens across your carbonyl double bond gives you that reduction to alcohols. Okay, so now we can use hydrogen, but we want to use specific reagents that only react with the carbonyl. Okay, so we have a specific compound that only reacts with carbonyl, and they're called sodium borohydride and lithium aluminum hydride. Okay, these only react with carbonyls, and there is some selectivity between the two. Lithium aluminum hydride is more reactive than sodium borohydride, and it reacts vigorously with water. The sodium borohydride, we typically run the reaction in an alcohol. So it is not as basic and it needs the alcohol to help the reaction progress. Okay, but the lithium aluminum hydride is much more reactive and will actually decompose down to 4 equivalents of hydrogen gas plus an aluminum lithium oxide, hydroxide. Okay, so because there's a reactivity difference there, the lithium aluminum hydride is more reactive and reacts with water. We can use that to our advantage to be selective about which carbonyl compounds we reduce and which carbonyl compounds we don't reduce. Okay, so I'm going to look at this other side first here, this what we can reduce with sodium borohydride. So like, our 2 primary carbonyl compounds we talk about are aldehydes and ketones. Sodium borohydride will transfer the hydrogen here, and I'll talk about the mechanism in a minute, to the carbonyl compound, giving us 1 hydrogen on this side and 1 hydrogen on this side eventually, and giving us our alcohol. Our aldehydes will always give us primary alcohols. Our ketones will always give us secondary alcohols. Okay, so that's different than that attacking with the Grignard reagent. If we had a ketone and we attacked it with a Grignard reagent, we get a tertiary alcohol. So we have a new way of making a secondary and a primary alcohol. But notice that the ester and the carboxylic acid are higher oxidation states, and they are not reduced by the sodium borohydride. Okay, so that's kind of cool because let's say you had a carboxylic acid or an ester and a carbonyl on your compound. If you chose the sodium borohydride, it would only react with the aldehyde or the ketone, would not touch the ester or the carboxylic acid. That's what we're talking about when we're talking about selectivity of reaction. And this will become very important next semester when we start adding more and more functional groups and wanting to do reactions on just certain parts of the molecule. Okay, so now let's look at the other one, the lithium aluminum hydride. It's much, much stronger. So it'll do the exact same reactions with the aldehyde and the ketone. It'll take the ketone down to a secondary alcohol. It'll take the aldehyde down to a primary alcohol. But it will also react with carboxylic acids and carboxylic acid esters. And in both cases, it's going to convert them to primary alcohols. And the byproduct for the ester, at least, is going to be another equivalent of whatever that alcohol was. And the byproduct here is going to be water. So we're able to take esters and carboxylic acids all the way down to primary alcohols, but only with lithium and aluminum hydride. So we're looking at that selectivity of reductions at that carbonyl. Okay. So again, we might want that selectivity. Let's say we had this compound here with our a double bond and a ketone in it. We can actually reduce down that carbonyl to an alcohol using our reducing catalyst of hydrogen on palladium, platinum, or nickel. So we can use that same type of hydrogenation that we use with alkenes and alkynes, and it will also reduce down that carbonyl. However, it'll reduce down the alkene and the carbonyl. Okay. What if you only want to reduce one or the other? Okay. If you only want to reduce one or the other, we have to be more selective about what we're going to do. So in that case, we would want to use, let's say if we wanted to keep the alkene, we want to use something like sodium borohydride to just reduce down the carbonyl. Okay. So we could use either sodium borohydride or lithium aluminum hydride, and the alkene stays intact. Okay, so that's because the lithium aluminum hydride and sodium borohydride only attack carbonyls, will only add across carbonyls. Okay, so let's talk about the mechanism. The mechanism I kind of didn't tell you about at first, but let's talk about it now. In sodium borohydride, we have something that's very important in here. This is the first time I think we've talked about it. We have what we call the hydride ion, okay? So the hydride ion is a negatively charged hydrogen. We've worked with diatomic hydrogen. We've worked with hydrogen as a proton when it's attached to other things. Now we're going to talk about the hydride. That is a hydrogen with 2 electrons on it, giving it a full negative charge, okay? So if it has a full negative charge, that makes it a nucleophile. And so we're going to use it as a nucleophile to attack our system. Okay, so let's blow this part of the reaction up. And luckily, we know that nucleophiles attack the carbon of the carbonyl. And so we have a great target for our hydride to attack. So the first thing we see happen is the electrons that are binding the hydrogen to the boron reach out and create a new sigma bond with our carbonyl carbon and kicks up to give us our oxygen as an anion. Okay, and what happens at that point is this is probably more basic, or maybe about the same basicity as our solvent in this case, which is ethanol. And so this gets protonated and generates a complex right here, gives us our alcohol alkoxide and our reacted material here. So that will give us an alcohol here, but now we have an alkoxide. And now we have a boron without 4 things around it. And so what we have happening here is we have a nucleophile and we have a Lewis acid. And they're going to react to form a complex that gives us this alcohol. And we still have 3 hydrides on it. Okay. Now, those 3 hydrides are just as reactive as they were before. And so what we're going to do is we're going to keep reacting those hydrides again and again and again until all 4 hydrides are removed from the boron, and we have 4 alkoxides hooked to that boron. So what we can do is we can use 1 equivalent of sodium borohydride to reduce down 4 equivalents of a carbonyl compound. Okay. And at the end of the reaction, when you add water, everything gets protonated and you can isolate your newly formed alcohol. Okay, questions on that mechanism? The key to the mechanism is that hydride. That hydride is our nucleophile. And the rest of the mechanism goes along with all of the other mechanisms where we have the attack by the nucleophile first. Okay. All right, don't forget chat rooms open for questions as well. Okay, so in lithium aluminum hydride, it's a little different because we don't have that alcohol contributing to the reaction. So it works a little differently. And so let's look at that. So if we add, but just like the sodium borohydride, it does have 4 hydrides to transfer. And it will transfer all of those hydrides, but it turns into a slightly different compound, okay? because we don't have that alcohol to displace or protonate the substrate we just reacted, so it stays hooked to the aluminum until the end of the reaction when we add acid. So let's look at that step by step. So we have, of course, our electrophile here. We have our hydride, again, using both of those electrons to make our new sigma bond. And then we have to counterbalance that negative charge on the oxygen, and it does so by reacting with the aluminum. Okay, so we have, again, 4 bonds to that aluminum with that negative charge there. And so it's counterbalanced with our lithium. Now, there's still 3 more hydrides. And so that reaction progresses and gives you the second one on there. So now you have 2 alkoxides bound to the aluminum, counterbalanced by lithium, but you still have 2 hydrides. So the reaction keeps going and going and going until you have all of those hydrides reacted, and you have this aluminum complex with 4 alkoxides on it. Okay, so at this point, all the hydrides are consumed, and we can quench the reaction by adding acid. When we add the acid, it's going to protonate all the alcohols here and convert that aluminum into aluminum hydroxide, and the counterbalancing lithium is going to be the lithium hydroxide. Remember, when we're doing with the acidic workup, the water is transferring a proton to the alcohol, leaving a hydroxide left over. So you'll see we actually have 4 hydroxides at the end of this reaction because we had 4 protons transferred at the end of that reaction. All right. So that means we can write a little bit easier if we do the overall reaction as giving this compound here, this 4 of these groups attached to aluminum, and then our workup giving us our primary or secondary alcohol. And just like with sodium borohydride, if it's an aldehyde, it gives you a primary alcohol. If it's a ketone, it gives you a secondary alcohol. All right, questions on that? Now, it is more reactive, so it does react with carboxylic acids and esters. So let's look at that mechanism because it's a little different. Okay, the first step is the same, where we have the attack by the nucleophile to give us our intermediate. Okay, so our nucleophile in this case is the hydride, and I'm going to blow up the bottom mechanism here. To give us our intermediate state here, we have our alkoxide bound to our aluminum just like before. However, we have an opportunity for the regeneration of our carbonyl compound by kicking out an alkoxide. Okay, when we kick out that alkoxide, it can actually bind to the aluminum, giving us a species with still 3 hydrides on it, but regenerating our carbonyl. Okay, now that we've regenerated our carbonyl compound, and notice this carbonyl is an aldehyde. Okay, we took this OH off and we replaced it with a hydrogen. So that's the first hydride transfer, kicks off the alcohol and makes it into an aldehyde. Well, now we have an aldehyde. We know we can reduce that with hydrides. And so what we do is we go ahead and react that hydride. So we've added a second hydride to the compound to give us our aluminum complex. And it'll transfer as many hydrides as needed, and giving us our final alcohol, which is the desired alcohol, plus whatever the alcohol of the ester was, plus the hydroxides. Okay. Notice that because we've transferred 2 hydrides in this ester reaction, it's not a 4-to-1 ratio, it's only a 2-to-1 ratio. So 2 equivalents of the ester to 1 equivalent of the lithium aluminum hydride will generate our final product. Okay. And likewise, if we do, the mechanism changes again slightly when we reduce down carboxylic acids. Okay. But the first thing that happens is we have an acidic proton. So the first thing that happens is our acid-base reaction. And our acid-base reaction basically deprotonates that. This is the hydrogen that's positive. This hydrogen's negative. And so we end up with hydrogen diatomic or hydrogen gas. Okay. And our salt of our carboxylic acid. So the first step is always that acid-base step. But we still have aluminum with hydrides on it. That aluminum with hydrides will act as the nucleophile and go ahead and react with our carboxylic acid salt, generating our tetrahedral intermediate. Okay. So we have an opportunity here too, in the fact that we can use the lone pairs on that oxygen to kick in and reform the carbonyl and kick out an aluminum oxide product with 2 hydrides left on it. So we've generated an aldehyde from our carboxylic acid because one of the carbonyls has been replaced with a hydrogen, but then we've generated another carbonyl compound, and then we have 2 remaining hydrides left. We can come in and act as a nucleophile to generate our primary alcohol here, salt. And then once we have that primary alcohol salt, all of the possibilities of reaction are done, and we only have to work up the reaction with acid. Okay, so it's a little different. It's again 2 equivalents to 1 equivalent on this, but the lithium aluminum hydride will reduce down esters and carboxylic acids. The sodium borohydride won't. Okay, so that's the key in the selectivity between those 2 systems. All right, questions on that? Okay, so we've learned 2 new ways to make alcohols. You learned that we can do a nucleophilic attack by a very strong carbanion, and we learned we can selectively reduce down the carbonyl using lithium aluminum hydride or sodium borohydride, and we have selectivity between the 2. Okay, so our next thing that we're going to do is we're going to look at reactions of alcohols where we're going to oxidize them down. Okay, got about 3 minutes left, so I think I want to hold off and start this on Monday. So I'd like to open the floor to questions about Grignard reactions, the carbanion, using hydrogen as our new nucleophile, using that hydride ion as our new nucleophile.
Where could we go to get more examples of these?
Okay, there's a lot more examples in the book on Top Hat and in the homework. And in addition to that, there's a big table in, it's online somewhere. Just look up reduction of carbonyls with hydrides, and there's this big table.
Sounds good, thank you.
But they do a lot more of examples in the book online. Oh, also SI sessions. We're going to be talking about those in SI sessions as well. And as well as Nick is also going to be covering something about the reaction tables I discussed earlier.
Yeah. And that actually reminded me, there will not be any SI sessions next Thursday and Friday, of course. Happy Thanksgiving. I will be enjoying mine with my family. So no SI sessions next Thursday and Friday, but Monday and Tuesday, we will be doing a review on radical mechanisms and all that good stuff. So if you can, please try to go to at least one of them next week. And hopefully it'll help you understand those chapters a little bit more.
And then the ones in December, we're going to talk about those reaction tables and these kind of reactions as well. All right, any other questions? Well, we're right here at 10:50 according to my table here. So what I'm going to do is I'm going to stop recording, and if you want to hang back and ask questions, or please do. If not, go ahead.